this show on the road or the circus?
Calc 1, chapter 9 of Calc 1. Okay.
Hello and welcome back to Differential Equations. We're starting chapter 3, power series solution to differential equations. This used to be one of the go-to methods because you can you expand using power series and then you figure out the answer, which gives you some kind of sequence of numbers at the end, which you can hopefully plot to the best fit curve or something and figure out the solution to the differential equation. So first we review power series. The power series are defined through Cn x to the n. These are polynomial power series. They are infinite, so 0 to infinity. And these polynomials are C0, C1x plus C2x squared plus C3x cubed plus ... going to infinity. So that's the power series. You can also say power series expansion. And power series are very useful because what they do is they turn transcendental functions, which you learned in pre-calculus courses, into polynomial functions. And we know that polynomials are easy to integrate, easy to differentiate. They're not easy to find roots, but we can deal with that, right, deficiency rather than worrying about integration and differentiation too much. So some of the power series that you know by heart are, say, e to the x. So power series for e to the x is the power series 0 to infinity of, can anyone remember? Exactly.
X to the n over n factorial.
Perfect. X to the n over n factorial. So that is the power series for e to the x, and that power series is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... This factorial, if you don't remember, so this n, this is read as n factorial, not as n. So that's just a multiplication, 1 times 2 times 3 times 4 times 5 times, and it goes all the way to n minus 1 times n is the n. So 4 factorial is simply 1 times 2 times 3 times 4, which is 24. Yes? Oh yeah, it disappeared. If you watch the... Yeah, when it doesn't sync immediately with the one node, with the one drive or whatever. Yeah, one drive, it erases the stuff. So whenever you see something missing, yeah, exactly. Have to always keep in mind. Just yeah. Other power series which you guys know by heart are expansion for sine x, cosine x. So summation 0 to infinity, you got that one. Negative 1 to the n times x to the 2n minus 1 over 2n minus 1 factorial. And this one works out to be x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus ... going forever. Another one that you know by heart is the cosine x, which is summation of 0 to infinity negative 1 to the n of x 2n over 2n factorial, which is going to give you 1 minus x squared over 2 factorial plus x 4 over 4 factorial minus x to the 6 over 6 factorial plus ... forever. You can see from these definitions that your sine is odd function. Its expansion is only odd exponents, and the cosine is even function, has only even exponents there. Now, the other two functions that are very easy to remember, since you know these two, are hyperbolic ones, which we use as well. And those two will be exactly the same, except you don't have the alternating term. So for sine hyperbolic x, you will have the same power series, 0 to infinity, and it's just x to the n 2n minus 1 divided by 2n minus 1 factorial. And the terms are x plus x cubed over 3 factorial plus x5 over 5 factorial plus going on forever. And finally cosine hyperbolic x, again same as the cosine x, no alternating term. So 2n divided by 2n factorial, which is 1 plus x squared over 2 plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial plus dot 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 forever. You can put 2 or 2 factorial, it's the same, right? Because 2 factorial is 2 times 1, which is 2. When we saw differential equation using power series, one of these patterns might emerge, and then you see the pattern, and then you write the corresponding function. There are other power series that might be useful along the way, but these are the the top 5. Now, power series operations. We need to know how to add and subtract power series, which is technically how to factor, right? If you understand the notation for power series, let's say you have summation of a x to the n plus summation b x to the n. Well, if you write these terms out, you are going to start, this is an and bn, so you will start with a0 plus a1x plus a2x squared plus dot dot dot, and then you have the plus, and then you have b0 plus b1x plus b2x squared plus dot dot dot. You see that you can put together a0 plus b0, and then plus, and then a1 plus b1, and then x, and then plus a2 plus b2, and then x squared, and so on. So these guys combine into summation of an plus bn x to the n. So you can put two series together. Now what's important is to have, I'll write it in blood, need to have the need to have same counter and exponent. Now what does that mean? That means that if you have summation of 0 to infinity of anx an x to the n, and then you have plus summation of, let's say, n xn minus 1 from 1 to infinity, we cannot add. And we cannot add because they don't have the same counter. One starts at 0, other one starts at 1. And they also have different exponents. One is n, the other one is n minus 1. So we need to perform some kind of witchcraft here to get them to be the same. And at that point we can add. So what we do is we do the procedure that you guys learned in your Calc 2 class, which is called shifting the counter. Now, you learned this procedure in Chapter 8, actually, in geometric series, but we are going to use that procedure now. So what's happening here is that you have your summation when n starts at 1 and goes to infinity of n, a, n, and then x to the n minus 1. And we know that we need to have counter to start at 0, so I'm going to subtract 1 on both sides to make this and get n minus 1 equal to 0. And from here, I see that I need to define that k is n minus 1. So now, my new power series, when I substitute k in, see k is equal to 0. But now all of your n needs to shift to k's, and this single n that used to be, now has to be k plus 1. So n becomes k plus 1, right? N is k plus 1 from the transformation. So this n becomes k plus 1. You have your a, and this a was an, so now it's a k plus 1. And you have your x, and now you have n minus 1 is k. Oh, beautiful. Look at that. We went from having a off on terms to having it line up the counter and line up the exponent as well. And we just now rename into n equals 0 to infinity, n plus 1, a n plus 1, and x to the n. Looks like we're already losing people. So now, when we plug everything back in, we have 0 to infinity, a n x to the n, plus summation 0 to infinity, n plus 1, a n plus 1, x to the n, and we can add to get summation 0 to infinity of a n plus n plus 1, a n plus 1, xn.
So wait, that first black line right there, what was that?
That's the problem.
Oh, you just copied that?
I copied, and then instead of the second one, I put in the, right, for the second one, I put the one that I renormalized. So now when they have the same start at 0 and they both have x to the n, we can add the inside. And we are going to call this recurrence relation. We are going to use this to solve the equation eventually. So adding and subtracting power series, you have to have the counter start at the same place, and you have to start the the same exponent.
How are you able to
I just changed the k to n. Yeah, I know it bothered me when I was. It just changed, but you see they are the same. They are the same equation. It just changed the name. So numbers that you get from here and numbers that you get from here will be the same numbers. Yeah, because I need n's to put them together.
What does that mean? You need n to put what together?
The two. Because,
Two equations?
yeah, so when we are starting the problem, we want to add these two, right? That's the symbol in between.
That's what we're trying to do.
So now, yeah, you want to add these two, but we can't add because they start with a different value. This one starts at 0, this one starts at 1. So I have to shift the counter to make them the same. And also I see that the exponent is off, so I have to worry about that one as well. So by doing this, we came up with the equation, as you can see, that starts at 0 and it has x to the k. Now, to add these, I just rename k's into n, so I can add n's two n's. That's all I did. I just rename. I can use whatever variable I want. Another thing that will be very useful when you run into Euler's equations are the fact that you can, if you have x to the x squared multiplied into 0 to infinity an x to the n, this one actually goes inside, and you get summation 0 to infinity an x to the n plus 2. Because this x squared is multiplying the entire series, so it distributes over every term. So this is another trick skill that you will need as you go through entire calculations for this. So you can bring in, right? And that's really useful, because you'll see that as you take derivatives, these counters shift by 1. And this term is in front of the second derivative, so that term really helps as we are doing these problems. What else is crucial? It's all about okay. And now it's time to take the derivative of power series. So let's say that you have the power series. Well, first, the derivative of power series in respect to x is going to be series that starts at 1. You copy the coefficient, which is Cn, and then derivative of x to the n is n x to the n minus 1. We haven't learned anything new here. You still have the same derivative of x to the n is n x to the n minus 1. You still copied the constant. So we haven't done any new mathematics. What you have to remember is that the counter shifts from 0 to 1. So every derivative you take, the counter will shift by 1. So the second derivative shifts it one more time, and it will start at 2. The third derivative shifts it one more time, it starts at 3, and so on. So now you can write this as nicer, as 1 to infinity n Cn x to the n minus 1, and I'm just going to say over here need to shift. And you know what that means. That's the blue procedure. Because your differential equation adds and subtracts these terms, right? So, and we know that we can only add these power series terms if they have the same counter. They all start at 0, or they all start at 1, or whatever number. So if you have a differential equation, you have to worry about those things. The second derivative of power series, right? You look at the first derivative and you take the derivative there, so that's going to be summation now 2 to infinity, then you have the n from the last time, then you have n minus 1 from the new one, copy the coefficients, and then n x to the n minus 2. Because the next derivative, right, it goes minus 1 on the exponent again.
Question, the n minus 1 was just the exponent from the...
Yes, from here. Okay. When you take the derivative of this one, the power goes down and you subtract 1 from it, right? So calc 100%. We copied NCN. NCN is the constant that we copied from the last time. The third derivative, we don't have any problems going past the third derivative. We could. Is summation 3 to infinity. Now we have n minus 1, n minus 2, copy Cn, and then the derivative goes one exponent down, so n minus 3. In order for us to, again, use these guys, we have to shift the counter and make them all line up. So now, as a quick review, say you want to take the derivative, or this is what you can do if someone from Calc 1 asks you, what is the derivative of sine x? Whew, good thing you asked. All right. What is the derivative of sine x? You immediately tell them that the expansion for sine is negative 1 to the n x to the 2n minus 1 divided by 2n minus 1 factorial. Right? In which process you need to explain everything about power series, factorials, and everything else that Calc 1 students don't know. Once you do that, you know that when you differentiate your power series, the power series will copy the constant. So now we shift by 1, right? So that's 1 that you shift. And then you copy the constant term, which is negative 1 to the n. And now you differentiate x to the 2n minus 1, which is 2n minus 1, right? And you have the x to the 2n minus 2 as the, I don't know why I put these parentheses here, don't need them. 2n minus 2, everything divided by, and we copy the 2n minus 1 factorial, right? 2n minus 1 factorial is copied. But we know that the 2n minus 1 factorial, well, let's leave it there for now. So now, how do we show that this is actually cosine? Because the formula that you see in front of you doesn't really look like the cosine expansion. It will in a minute, right? What we do is we take the 2n minus 1 and 2n minus 1 term, and they cancel. So we have negative 1 to the n. That's the one that looks good. And now when we cancel the term from here, 2n factorial stays because that's the next term. Sorry, 2n minus 2. Or 2n. Minus 1. Yeah, 2n minus 2. That's the one term before. So this stays as x to the 2n minus 2 over 2n minus 2 factorial. And now you want to bring the counter back to, 0. So now remember, now we're going to do blue procedure one more time. So this is n equals 1. We know that we need to subtract 1 on both sides, from where n minus 1 is equal to 0, so call it k. This n minus 1, call it k, from where n is equal to k plus 1. And now plug all of these up there.
Oh, wherever you see the n, you change it to k plus 1?
K plus 1, yes. So we have the summation of k goes to 0 to infinity. We have negative 1 to the k plus 1. And then we have x to the, and now you have 2 times k plus 1 minus 2 divided by 2 times k plus 1 minus 2, everything factorial. Summation, k goes to 0 to infinity, negative 1 k plus 1 divided by x. And now, when you distribute over here, you get 2k plus 2 minus 2 is just 2k. And you get the same thing on the bottom. And there's your cosine. You can try to work this procedure out with your hyperbolic functions. You can show that the derivative of e to the x is e to the x by simply running this. So you will have to shift the counter every time because counter shifts every time you take the derivative. Since we are not going into the theory later on in the chapter, we don't have to worry about the radius of convergence, but if you want to find the radius of convergence of power series, you just unleash the ratio test. And it gives you. And they actually solve one differential equation as an example in 3.1. But that's what we do in 3.2 and 3.3. So I'm just going to end this review session, which is 3.1. I'm going to end it here, and then we're going to go and solve differential equations now in 3.2. That's it. See? People are happy.
I'm so excited to do that.
I know. Actually, maybe you know what? Before let me do a very quick, basic problem that is, as an example in 3.1, because as I see over here, 3.2, they immediately go second order, right? So I understand that we can do the first order equations, right, with this as well. Guys, technically this is a sledgehammer, right, to solve differential equations. And when you're putting up a picture frame, right, which is equivalent to the first order linear equation, you don't use sledgehammer, but you can, all right? So that's what I want to do now. Let's solve very simple equation. Let's say y prime minus y equal to 3. Whatever. You can solve this with separation of variables easily, right? You add y to the other side, and then you just do the, right? Now, this is going to be a power series solution to this equation, and we are going to put the power series here. Now, should I use? Yeah, okay. So we assume solution y equals summation 0 to infinity Cn x to the n. So we assume some kind of a solution here. Now, see, that solution assumes all of the functions that we can get in expansion. It assumes exponential, trigonometric, logarithmic, any type of a binomial, right? Whatever you have as a solution, it's assumed under that thing. And we know that we can plug that for this y. That's great. So I need to differentiate this so I can plug it for y prime. So when I differentiate this, I get 1 to infinity n Cn x to the n minus 1. And now I need to shift the counter to get it into the form where I can plug in and get the recurrence relation. So y prime with a shifted counter, 0 to infinity, right? We have k would be n minus 1. So n is k plus 1, so this is k plus 1, ck plus 1, x to the k. And then rename it 0 to infinity n plus 1 Cn plus 1 x to the n. So now you have this, plug in. What do we get? Instead of y prime, I'm writing summation 0 to infinity n plus 1 Cn plus 1 x to the n minus summation 0 to infinity of Cn x to the n equals to 3.
your brain must know exactly how you write it so fast.
I actually solved this equation already.
So wait, that's
dragging
you
my
have
feet.
The red star.
Those are the ones that I'm plugging
Why
in.
is it not k plus 1 and then you went back to n plus 1?
I went back to n so they match, right? I need to match n with n. I can't factor xn and xk, right? They have to be xn, xn. I'm changing this equal to 3 into equal 0. We do the homogeneous case real quick. So now, when you are subtracting these guys, you see that you have x to the n and x to the n. You can factor those out, right? So summation 0 to infinity, and what we get is n plus 1, cn plus 1, minus cn, x to the n equal to 0. Yes, yes, you replace those. I changed it equal to 0. All right, so now what we do is we have this recurrence relation, which is n plus 1, cn plus 1 minus cn equal to 0. From here, we see that cn plus 1 is equal to cn over n plus 1. This is the equation that we can use to calculate all of the coefficients, right? So where do we start? Now this is a little bit convoluted, so pay attention. We start with calculating with n equals to 0. When n is equal to 0, you plug that into this recurrence equation over here, we get C1 is equal to C0 over 1. So C1 is equal to C0. When n is equal to 1, we get C2 is equal to C1 divided by 2. So we see that C2 is equal to C1 over 2, but C1 is C0, so we can also write it. I don't know which one we're going to need. I'm just going to write both of them. We're going to need one of them, either C1 over 2 or C0 over 2, but let me write both for now. For n equals to 2, it's C3, right? I'm plugging n equals 2 for n. So 2 plus 1 is 3. So C3 is equal to C2 over n plus over 3. So C3 is going to be, oh, we're just going to need C0. Okay, so C0 over 3. Because oh no, hold on. C2 is equal to C0 over 2 over 3. So it's C0 over 6. There we go. Yes. So now n equals to 3 is C4 equals to C3 over 4, and then C3 can be written as C0 over 6 and then over 4, so the whole C4 deal is C0 over 24. And let's do one more, because we can. N equals to 4, which is C5, which is C4 over 5, which is C4 is C0 over 24 over 5, so C5 is C0 over 120. This can go on forever, but if you already see the pattern of what's happening on the side, that's where you can stop. We see that every single one of these can be written as a C0 divided by a value. And that value in this case is 1, 2, 6, 24, 120. What is this string? What is the string? 1, 2, very good, n factorial. 1, 2, 6, 24, 120. That's n plus 1 factorial. It's n plus 1 factorial because you need to start with another 1 in front. That's a 0 factorial. But we don't have it. We start at 1, 2, 6. So you remember that your counting starts at n equals 0. So we have 1, 2, 6, 24, 120. That's n plus 1 factorial. So I am able to write the entire string of these CNs as C0 divided by n plus 1 factorial. Now, how's this relevant? Well, I found the only unknown thing which I had, and there were coefficients. Remember that I assumed the solution, which was summation Cn. Summation Cn x to the n. But now I know what Cn's are. It's a C0 over n plus 1 factorial. And then, I'm missing the summation, I'm missing x to the n. There we go. Now C0 is a constant. So that escapes in front. And I have summation of x to the n over n plus 1 factorial, which is going from 0 to infinity. Now, this is the solution. Can I actually figure out some kind of a function out of this? Well, if this was x to the n, and this was x to the n, and this was n factorial, it would be e, right? Do we all see that? Because you know the power expansion. There we go. But it's n plus 1 factorial. Now, what can I do? I can peel off this n plus 1 term. So, what I can do, using algebra here, is write C0, summation 0 to infinity, x to the n, and then over here I have n plus 1 times n factorial, which, again, using algebra, is 1 over n plus 1 times x to the n over n factorial.
Peeled off, what did you say? I missed that part. You peeled off the
n plus 1 from the factorial. Yeah.
From the denominator?
Yep. And stays with n factorial. What happened?
You just convert that to UDX.
Trying to see if I can. This is dy dx equal to y. So we have ln of y equal to x plus c, and this is e, and you e both sides, it becomes y equals ae to the x. This term is bothering me here. Just need to make sure that I didn't make any mistakes along the way, but
Once we do get that DifEq, doesn't the sum of all the one over x response affect one number? So go back to here, you can see. The summation of 1 over x plus 1 is weird. I don't know. I'm assuming it does. Okay, I guess it does. It doesn't. I don't know.
Exactly, from scratch. I have to downgrade some grades over here. All right. There is something here that happened somewhere that I missed, and that's all. No, this is all good. This is y over there, cn, n plus 1. Yeah, n plus 1, n plus 1, cn plus 1, next to the n, put them together. Cn is cn over n once, good. 0. Oh. Oh, no.
What about when you did that second, when you said assume, the second derivative, where you changed?
There are no second derivatives here, it's the first derivative.
You copied where after you said assume.
That's the beginning of the problem.
Right there. When you said that k, that's supposed to be n plus 1 over there. Again on the bottom, below that red star.
Yeah.
So again, right there. C summation n plus 1 and then c n plus 1.
Next to the end, yep. That's when you shift. This all looks good.
Maybe it's not n plus 1 factorial.
So isn't the shift supposed to be 1? It's twice of 0 again.
Yeah, what if it's 1?
But this is 1 factorial, this is 2 factorial, this is 3 factorial, it's 4 factorial, it's 5 factorial. And if your series starts at 0, then it has to be n plus 1. So having that as n plus 1, this is why you don't use sledgehammer on the simple problems. Because when it doesn't work, you go crazy, everything is correct and it doesn't.
That's a c, the n plus 1. Oh, wait, no. You converted that to c to the n plus 1 equals c to the n over n plus 1 factorial? But in volume, that's not what.
Yeah, I'll have to meditate on this one to find what is wrong. But we do see e to the x and we do see c0, which are these two components. I just need to see what is going on with this term over here, which I don't like at all, factor actually in this case. So I'll figure it out and we'll come back. Well, the goal is to actually go and work on the second order, so make these problems a little bit longer and.
Make them more difficult.
There is something over here. There's probably something here at the end that I'm overlooking. I'm just. Yeah. When I stop thinking about this, it will work out. So I'll restart the stream for the next section, and as soon as this clicks in, I'll go back and fix it. That's how it usually goes.